Hello. My name is Wanak Kwan. I work as an SoC developer at the Electronics and Telecommunications Research Institute, ETRI, Digital Holography Lab. We will introduce research on real-time holographic media systems using FPGA. Many of the future technologies introduced in the movie have become reality. However, the holograms from Star Wars 40 years ago are still difficult to implement. I hope the real-time holographic media system I am announcing today will be a starting point. This slide is a simple illustration showing the operation of our real-time holographic media system. Our holographic media system generates any 2D video into a 3D hologram in real time. Let's take a look at a more detailed system configuration diagram. Packet Gen's input is mainly classified into three categories. First, it is a pre-made RGBD data input. Second, it is an RGBD camera input like MS Edge or Kinect. Third, RGB input like YouTube video. At this time, depth is generated in real time using a depth estimation monocular model. The RHP processor receives RGBD data through Ethernet or PCIe. RHP generate an off-axis 8-layered 30 frames per second CGH in real time. RHP outputs to SLM via 4K HDMI interface. If videos have sound, RGDB plus sound packets are created. RHP can play holograms and sounds together. RHP implemented a volume hologram by applying a layered algorithm. It is displayed in 8 different positions in a holographic reproduction optical system. First, let's look at the theory and algorithms applied to RHP. Modified off-axis Fresnel propagation equation is used in RHP. The propagation equation is as follows. For hardware implementation, the floating model was modeled as a fixed model using MATLAB. RHP uses a layered holography algorithm to express three-dimensional holograms. The layered holography algorithm splits a 3D image into 2D layers of varying depths, enabling faster generation of high-quality holograms, ideal for applications like holographic video. Let's take a look at the RHP hardware structure. First, the RHP core structure. The single-element holography processor, SEHB, which processes single-layer CGH, consists of a processor core and a memory core. The RHP core is a SEHB scalable structure, and the number of layers that can be processed is determined by factors such as frame rate and FFT size. RHP has a total of 2448 SEHB cores in 3 colors and an 8-layer structure. RHP's memory handling is the most important hardware part. When performing 2D FFT, the row-wise FFT result is stored in memory, and then the and column-wise FFT is performed. As the FFT size and number of layers increase, the memory to be processed per frame increases. As shown in the figure, memory capacity and speed in FPGA are inversely proportional. To store 2 or more layers of row FFT, HBM and DDR4 memory are required. In 2D FFT operation, colorum-wise operation takes a lot of time due to discontinuous address read operations. For this reason, high-speed memory is required in RHP. Multi-channel HBM memory is the optimal solution for high-speed 2D FFT processing. This slide shows the hardware architecture of RHP24. RHP input is PCIe or Gigabit Ethernet. The output is 4K HDMI, which is the SLM input interface. PCIe, Ethernet, HDMI, DMA, microprocessor, etc. used Xilinx IP. User logic includes RHP24 core, downscaler, and upscaler logic. The memory used was HBM with 11 channels, 256 megabytes per channel. Hardware blocks transmit data through EXI bus. They communicate with the microprocessor through the EXI Light bus. RHP has been developed over the past 3 years. RHP22, version 1, developed in 2022, is designed as a single-core SEHB. RHP23 adopts RGBD packet type hardware structure to achieve 4-layered, 15 frames per second performance. RHP24, developed in 2024, supports RGBD plus sound packets. 8-layer, generates 30 frames per second off-axis CGH. The optical holographic reconstruction system adopts a viewing window method. A 3-inch lens with a focal length of 50 centimeters was used. Viewing window of 13.8 mm was obtained by arranging the SLM and lens. The 8-layer-based volumetric hologram generated by RHP system is optically reconstructed at 1.25 m in front of the SLM, with the volume thickness of 40 centimeters. The RGBD image on the right is explained as an example. In the RGB image, the letters D1 and D9 are in the black depth area. Therefore, the letters D1 and D9 are focused on the L1 layer. D8 letters with white depth are focused on the L8 layer. This slide is a demonstration of a real-time holographic media system. There is a Linux host transmitting RGBD packets in the center. The RHP FPGA board is connected to the Linux host via PCIe over Thunderbolt or Ethernet. There is an MS Edger Connect RGDB camera. The 4K SLM is connected to the RHP via an HDMI interface. The optical system consists of mirrors and lenses. An 8-layer hologram image is formed behind the lens. The video from the hologram camera can be viewed on the monitor. The packet transmission program includes RGBD packet transmission and FPS monitor, RGB image, and depth image. This slide shows the results of a preprocessed RGBD data input experiment. This is an 8-layer hologram photo of the RHP system when the RGB and depth images shown in the picture are input. Layer 1, depth color is black, focus on characters D1 and D9. You can see that the focus is on the D2 character in layer 2, the D3 character in layer 3, and the D8 character in layer 8. This slide is a hologram photo restored from the RHP system when pre-produced RGBD video data was input into the RHP system. The first image is rear focus, the next image is mid focus, and the next image is front focus hologram. This slide is a holographic image of the video input to the RGDB camera in real time. When you adjust the camera's focus in a still image, you can see changes in the image depending on rear focus, middle focus, and front focus. This slide is a holographic image that extracts depth from a YouTube video and reconstructs it in real time through the RHP system. As you adjust the camera's focus, you can see that the image changes to rear focus, middle focus, and front focus. The QR code below is a link to a demo video of the RHP24 system. Holograms still have a long way to go, as display technology faces many challenges. However, we hope that today's research can lay the foundation for the complete reproduction of holographic images in the future. Thank you.